the cross between two vectors. So if you recall, the dot is to say, okay, I give you two vectors, you produce me some scalar value, right? And we define it using the geometric perspective. But here, it's really different in the sense that we are going to produce a vector out of the two vectors B and C. And so let's introduce the formula for this cross, and we'll get in like some idea. Okay, so B is the vector B1, B2, B3. C is the vector C1, C2, C3. The cross product B cross C is defined by the following equation. So let me first write down the component-wise description in angle brackets. So it's B2 C3 minus B3 C2. That's the first component of your vector, the cross product. Okay? And then if you look at the second component, it's B3 C1 minus B1 C3. And now you see a kind of a pattern. But then it follows. So the third component is B1 C2 minus B2 C1. So one thing we can realize is that, okay, so every term within this formula is that's some number of B times another number of C, right? So you see B2 C3, B3 C2, B3 C1, B1 C3. So you don't really see B2 C2, right? So it's like the second component of B times the third component of C. So you don't really see the second component of B times the second component of C. So that's one thing. And another thing to observe is that in the first component of this vector, you don't really see the index 1. Right? So there are only two possible ways of constructing from B and C using different indices and just not using the index 1. Right? So it's only C 2, 3 or 3, 2 from B and C respectively. And the similar thing happens with the second component. There's no 2, and you see 1, 3, 3, 1 from B and C. And similarly, the third component does not have numbers index 3 in the formula. So these are two facts that may help you memorize this formula. And of course, in your handwritten notes in the exam, you can always just write that down, so you don't have to memorize it. But in this section, we're going to introduce you another way of representing the cross, which is a 3x3 determinant, where we put ijk, the center basis, on the first row, and we put the vector b on the second row, and the vector c on the third row. So this 3x3 determinant is essentially the same as the formula right above, but basically in this section we're gonna carefully define what it is. But this is probably something we'll do tomorrow. Okay, so roughly speaking, once we introduce the formula, you should be able to calculate a bunch of MyLab homework. So at least that's good for that part. But now it looks complicated, right? So let's start with the geometric perspective. Okay. Geometric point of view. On the cross product between B and C. So this is not entirely straightforward, so it will take us some time to get to this formula from the vectors B and C. So let's look at that. Okay. So consider in the three-dimensional space, we have three vectors. So you see, okay, we have B and C, right? So where's A? So if we have three vectors A, B, and C, essentially you'll be able to construct something interesting. So that's three vectors can form you a parallel pivot in this space. So let's say this is A, and let me say this vector just at the rear side of some figure in dash line is vector B. Okay, that's going to be C. So the B is the one in the front. So this is B. So that's C. Okay. So basically, we have B and C. If you draw the parallelogram for these two vectors, essentially you have a base. Of a parallel pivot. Yeah, well, yeah, let me try make it look better. But if you're sketching it, you can sketch it yourself, and possibly it's going to be better than here, right? Okay, why don't I just copy? No. Because I want to make dash. One last attempt. A little better. Okay, so let's call this head of B as cap B, a point in the space. And then this point is cap C, right? And this is the point D in the space. Okay, so now that's only the bottom side of the what's called a parallel pivot. And then we have a vector A, right? So that will give us a few more faces. One of them is the one in the front, but which is still I didn't realize. I do apologize for that. So yeah, well, I don't know how long, but usually it will pop out and just doesn't look good on the screen. So in the front we have a face which is parallelogram, and it will just extend all the way to the rear side. Okay, so the face in the front, the face on the long side, and then of course we have the bottom, which is OB DC, right? Then we have the top. Parallel pivot. So I think there's another way to read it as parallel pivot, but let's just read it as parallel pivot for my ease. Right. So basically, what do we want? We actually want the volume of this parallel pivot. Okay. So basically, from three vectors A, B, and C, we'll be able to form this solid in the space. And we want to get volume. So let us try to compute the volume sigmoid point to size. So let us try to compute the volume of the parallel pivot based on vectors A, B, and C. Okay. So if you want to do this, you want to somehow decide a base. So parallel pivot is nice in the sense that as long as you choose a base, let's choose the base constructed by B and C. Okay. So as long as you have the base and then you have a height, right? So the volume is just going to be the base times height. So, and then the base is what? The base is the area of a parallelogram. So it's SOB DC, right? But then you need a height. So what do we do about the height? So what we need is so for any point on this top parallelogram, the distance is going to be the same, right? So for whatever point on here, the distance to the base is going to be the same. So for that point A, we can just draw a orthogonal projection, and let's say this point is P. Okay, so orthogonal projection down to the bottom plane, right? And then so we have found the direction from A to P, right? So now let me just draw the vector which is along this direction, and it just goes up. And we call it U. Okay, so the direction here is that it's just perpendicular to the base plane, right? And then we can define the volume. Okay, so we can write down the formula. So V is going to be the area of the base times the height, right? The height is just the distance between A and B. Okay. Right. So let's just keep the directions in purple in the figure. Let's just continue. Area SOBEC. So basically, we don't really want the direction of the microphone to point at any of the speakers. Sometimes use it. So the area of the base actually SOBDC is not so difficult to compute because what do we know? We know that OBDC is constructed by two vectors, right? So that's actually B and C. So OBDC, that's vector B, that's vector C. So let's say the angle here is between the vectors is theta. Then what do we know? So instead of doing the cosine, we want to do the sine of theta, right? Because if you draw the distance from point B to the vector C, it's going to be the orthogonal projection. But we're looking at this height, right? So this distance is what? This distance is actually the magnitude of B, which is the hypotenuse, times the sine of the angle theta. Right? So now this distance in the dashed line is this B times sine theta. And now, what do you think about the area of this parallelogram? This should equal to what? Do we need something else to multiply? Right here. The area of the parallel one. What do you think? Is this correct? Not really, right? That's just height, right? It's just the dashed line distance, which is like a line segment. We need to multiply something to get the area. So what do we multiply? So, the magnitude of C. Do we all agree? The magnitude of C. Okay. So the length of this times the height right here. That's they're perpendicular, so indeed you will get the area of the base, the area of the parallel. Right. So that gives us this part, right? And then about the distance between A and P. So now let's think about that plane that is constructed from the direction of AP and our vector A. Okay. So just look at this figure right here. So this distance, well, this direction, what I have drawn is exactly the same as this distance. Actually, the direction. So they're just essentially two parallel lines. But then how are they related? So basically one of them is going through the head of the vector A. One of them is going through the tail of the vector A. So if I draw it in another figure, it's going to be like this. So we have the red vector A, and we have the purple perpendicular projection. So this is all, this is A. And then we have the parallel direction U. And then what do we know about this AP direction? The AP direction is perpendicular to the base. So we don't really need the entire base to be sketched, but so this OP direction is this so this part, okay, this part represents the base. Now, suppose that a vector U is perpendicular to the base OBDC, and the angle between U and A is phi. So basically, I'm saying here, now I have the direction AP and the same direction, well, the parallel direction U, right? So we have U and A. I'm going to give this angle as angle called phi. So you know from the fact that the vector U dashed in purple on the left is the same direction as the direction AP, well, it's the same direction as PA. So these two angles are essentially the same. Okay. And now, if you know this angle is phi, then from the magnitude of the vector A, this hypotenuse, you will be able to get distance AP, right? So AP, the magnitude is what? It's actually the magnitude of A, the hypotenuse times now cosine, right? So it's the adjacent edge at this angle P. Does that make sense? Okay, so now we can put the things together. So we know this area of the base is this quantity, right? We know the height AP is this quantity, so we can just multiply everything together. Hence, the volume is SOBBC times the length of AD, and then we just write things in that column. Yes, I don't really want the dots. So it's the magnitude B and C sine theta times magnitude A cosine. So this portion is the, well, I don't really need to indicate it because, well, this bracket is the first term right here. This second bracket is the second term, AP, right? Now, notice that phi is what? Phi is the, you see, here we have the angle between A and U. We have the magnitude of A, right? So we decided, okay, this is the vector A. We have a direction U that we decided that's perpendicular to the base, but we haven't decided the magnitude yet. And if we decide this is the magnitude of U, then we decided the direction and the magnitude. Okay, so if we can get a vector U that has the first bracket here as the magnitude, that would be great. Since phi is the angle between A and U, if the magnitude of U equals to the first bracket which is the area of the base, then we can rewrite the volume of the parallel parapet as U dotting with A directly. Of course, in the case that the dot is not negative. So basically, as long as U is defined in this nice way, right, then that'll be good. Now, suppose that A has the components A1, A2, A3. B has the components B1, B2, B3. And C has the components C1, C2, C3. Let us find the components of U, which we just denote as X, Y, Z. So we have the vectors A, B, C, right? And then we need a vector U, which is first perpendicular to the base. Basically, the first has to be perpendicular with both B and C. So that's the first condition. That's the direction part. Okay? And we also know that we want this U have the magnitude of this. Okay? And we, by the way, we know the magnitude of B has the magnitude of times sine. That sine is always negative, right? When your angle theta is between 0 and pi, this sine value is always negative. So this part is definitely fine. That's the magnitude. Okay, we don't really have the worry that it may negative, but the angle phi is something else. So the two conditions we must meet simultaneously to get the coordinates of u. So let's try setting up the equations. So we have actually three conditions. So we need what? We need u to be perpendicular to b. So that's just saying the dot should be 0, right? And u has to be perpendicular to c. That means u dot c has to be 0. And then finally, so this is the direction part, okay? So u is perpendicular to the base, that's the direction. And then the magnitude, we want the magnitude to be exactly CB magnitude multiplied times sine theta, right? We have these three conditions. So as long as we satisfy, as long as our as long as our vector x, y, z satisfy these three properties, that u should be good. All right. Any questions for? So basically, we essentially relating the vector u as the vector that's perpendicular to b and c that we start with, and at the same time, the magnitude has to be the area of the parallelogram formed by b and c. And so essentially, we will get to the equation that we started with at the beginning of the section. But now to put them down in an analytical way, so putting the coordinates together, u dot b is what? U dot b is b1x plus b2y plus b3z equals 0, right? And now u dot c equals 0, that means c1x plus c2y plus c3z is 0. Okay, so we see, okay, these are linear equations. The third one is a little bit more complicated, so let's square both sides. So because we know that the magnitude is always under the square root, which is something we don't really want. Okay, so squaring both sides, it will get rid of the square roots. And at the same time, we know what cosine of theta is, right? We don't really know what the sine of theta is. But we can do the Pythagorean theorem to rewrite it, right? One minus cosine squared. So this bracket at the end can be distributed. So this is the magnitude of c squared, magnitude of b squared minus. So now, if we do the distribution, we have what? We have the magnitude of c squared, magnitude of b squared times cosine squared. And so we can put them together in a single bracket. So c, the magnitude of c, the magnitude of b, and cosine theta, whole thing squared, right? And now you see, okay, within this parenthesis, that's nice. That's just b dot c, right? So this is what? This is the magnitude of c squared, magnitude of b squared, minus, in the bracket we have b dot c, whole thing squared. Or c dot b whole thing squared. That doesn't really matter. Right? Okay, so now we are able to write the equations in a nice way because now everything is, so now every magnitude is like just the sum of squares, right? And then the dot is just the component-wise product added up. So we have the three equations. We have three equations with variables x, y, z. Okay, so three unknowns x, y, z are to be solved from the following equations. So let me put these two. Let's just copy. Let me make it black. And then finally, the last one is what? The last one is the magnitude squared is x squared plus y squared plus z squared. Now, the right-hand side, the magnitude of c squared is what? Is c1 squared plus c2 squared plus c3 squared. And now the magnitude of b squared is b1 squared plus b2 squared plus b3 squared. And then minus b dot c is essentially b1 c1 plus b2 c2 plus b3 c2. Okay, so equations 1 and 2, they are simple enough. Equation 3 is a little bit more, it's a little bit more complicated, especially on the right hand side. So here, the third equation is equivalent to the following. So notice that the squares, right? So we have c1 squared, b1 squared that we can multiply, which is something we don't really see in the equation that we start with in the section. c1 squared, b1 squared is not going to be there because what? Because b1 c1 squared is going to be cancelled out from the second square. So essentially, you will get something that's really nice. So we are motivating the equations that we started the section with. Okay, so what are we doing? If you look at this is a system of 3 equations, and the circled ones are actually, well, they're plane. Well, they are linear equations. They represent, later you will know that they represent planes, right? And then that's actually very reasonable because we said, okay, this u, this vector is perpendicular to B and C, right? So that's actually a ray. That's actually just a direction. So if you think about 2 planes intersect, that will give you a line, right? That's a ray. Okay, so that's something kind of reasonable. And the last one, this is saying, okay, my magnitude has to satisfy some equation. So okay, let's just say, okay, my point has to stay on a sphere, a particular sphere, right? So let's continue. So in fact, there's a way that we can simplify the right hand side, because if you look at the thing here, if you multiply things out, we have 3 terms in the first bracket, 3 terms in the second bracket. If you multiply things out, there will be 9 terms, which are complete squares. But also you realize that if you have index to be the same, like C2, B2, it will be cancelled with the square here. Okay, so that tells you what? It tells you there will be 6 term that's left for complete squares, which will be right here. Okay. And then what about the squares from the second bracket? Well, excuse me, what about the non-square terms in the second bracket? So in the second bracket right here, there will be squares b1 squared with the c1 squared, b2 squared, c2 squared, b3 squared, c3 squared, and they're going to be cancelled. And the other terms are the course terms. Course terms are in the middle, right here. And you see, I rearranged everything in a nice way so that in each bracket, in a particular row, that will give you a complete square. And if you really think about what are here in this bracket, actually, that's one component within the equation that we started with this section. Okay, one component of the process. So this is yeah, let me just write B2, C3. So although here in this term it looks to be B3, C2, but to be consistent with the order of the expression at the beginning of the section, B2, C3 minus B3, C2. Okay. And then the second component, B1, C3 minus B3, C1. And class 1, B1, C2 minus B2, C. Okay, so now this looks much better. So here I'd like to quickly mention that we're not really trying to derive the cross product out of the scratch. Here we're essentially trying to convince you guys that those things serve the purpose. Okay? Those components of the cross product serve the purpose of what we want. So we just put the things together. So we have the first two equations and the last one that's somehow simplified or rewritten at the top of this page. So I'm just gonna cheat a little bit by copy and pasting. And the third equation is going to be the sum of squares. And you see, the sum of the components squared on the left-hand side equals to these expressions. And I'm probably, yeah, want to do this so that it's not so spread out. Okay, so here it's getting there. Okay, so if you compare with the equation that we started with this section, if you call the components of the cross product formula to be x hat, y hat, z hat, so this is exactly x hat. Okay, the first component of the cross. This is negative y hat. Okay, so if you recall, in the y component is what? It's B3C1 minus B1C3. The order of the index is a little bit different. It's opposite. And this is d hat. Okay. So now we have the unknowns on the left hand side squared and added up equals to the known values taking the sum of squares, right? And that again. Okay, so now we have three equations, 1, 2, and 3. Let me put them. So yeah, okay, that's good. So let's somehow eliminate the z variable from 1 and 2, so that you will see things a little bit clearer. So if you do B3 equation 2 minus C3 equation 1, that will eliminate z, right? This will give you a linear equation with only x and y, which is B3C1 minus C3D1 x plus B3C2 minus B3D2, which is 0. Let's call it equation 4. Okay, so if you look at equation 4, you see, the constants in the front of x and y are pretty nice, because just like what we denoted for x hat, y hat, z hat. So this part is exactly negative x hat. This is y hat, right? So y hat x minus x hat y equals 0. So here so we're not really solving the x, y, z, but we're just trying to convince you that compare 3 and 4. We know that x hat, y hat, z hat is a solution. Okay, x hat, y hat, z hat as a tuple is a solution for x, y, z. We have an easy solution. So let's just we only need these three equations. So basically, x is negative of B3C2 minus C3B2, which is just B2C3 minus B3C2. Okay, we still put these up front. And y is B3C1 minus C3B1, which is, yeah, oh, we don't really need to change the sign. And z, okay, so basically xy, if we choose these two values, then equation 4 is satisfied. Equation 3, these are gonna cancel with these, and now you see, okay, z is somehow either z hat or negative z hat, right? And the thing is, if you plug back into equation 1 and 2 for the x, y, z values, only z hat can survive, okay? So that's exactly what we want. So one choice of the vector u is exactly that formula that we started in this section. Okay. B2C3 minus B3C2, B3C1 minus B1C3, B1C2 minus B2C. So note, this is an important note. Note that a different solution of the system is the components of the negative u. So just now I mentioned u right here. Yeah, let me display that system of equations once again. So if you choose these coordinates to be x, y, z, that will satisfy 1, 2, 3, right? But now at the same time, I'm saying, okay, if I flip the signs for x, y, and z all at the same time, then 1, 2 are of course linear equations, so they will be satisfied, right? And 3, the sign of x, y, z doesn't matter because 3 is a kind of a spherical equation. Okay, so indeed, negative u also is an option. Okay, is a solution from the system. So we somehow need to define the one that we want. So that's why we have a right-handed or left-handed coordinate system that we start with. But here to write it down, definition for any vector B with components B1, B2, B3, and C is C1, C2, C3. We define the cross product with underline of B and C by this equation. Okay. B cross C is, so we choose this solution to be the cross product. Okay. So basically, this is just a deciding one direction. Okay, we showed one. So concern. Components of either U or negative U would solve the system, right? So if you think about the system, once again, so it just have two requirements. One, the vector that you want, this vector U, has to be perpendicular to the plane that you start with. U has to be perpendicular to B and C. And two, U has to have a magnitude, which is the area of the parallelogram formed by B and C, right? But there are two possible directions. So we chose one, but how do we determine that from the geometric perspective? So that's the question. Okay. And so just like a quick side comment. So if you imagine what's happening, indeed there will be two solutions because the two linear equations, 1 and 2, that's an array, just like I mentioned. So this is just a line going through the origin. So that's the array, which is one-dimensional. And now the sphere, which is centered at the origin, right? So equation 3 is just a ball, right? It's the sphere. It's just okay. The magnitude has to be fixed. So intersecting, so if you put the three equations together, that's sphere intersecting with the array. So how many solutions do you think there will be? 2, right? So they are exactly symmetric with respect to the center of the sphere. So that's exactly why, okay, we have two solutions and actually they are exactly opposite. Okay, but we are, so that's kind of like the idea behind the scene. So definitely this kind of concept idea is not really required, but just you should remark. I star. It is important to distinguish B cross C and the negative of this vector. Okay. So because both of them are perpendicular to the original plane and both of them have the same magnitude. So we can distinguish the directions by the right-hand rule. So we say a system, a coordinate system, XYZ, follows the right-hand rule if what? If, so yeah, let's look at this screen again. So if you put up your right hand, the fingers go along the x direction, and you bend your fingers along the y direction, and then the thumb points at the z direction. Okay, so that's the right-handed system, right? So this gives you the relationship between three vectors. So that's going to be the same for a cross product. So mainly, your fingers go along the first vector b, and then you bend along the direction c, and then the thumb is pointing upwards. That's going to be the direction of the cross. Okay. And of course, the opposite direction is going to be downward, which is not the following your right hand. Okay, so that's the right hand rule. So to put them down in a figure. So let's say our vectors B and C are like this. So if you put them down in the plane right here. So let me stand up again. So if you assume that B and C, they are exactly this plane in front of you on the monitor, and then the four fingers go along the direction of B, you can bend along the direction of C, and then the thumb is pointing towards yourself, right? Pointing outside of the monitor. So that's not really easy to sketch. So one idea is that you just draw the symbol from physics, like circle with the dots inside. So this kind of illustrating this arrow just flying towards yourself. Okay, so that's the direction of B cross C. But of course, if I say that direction is the direction going upwards, that's still going to be fine. Okay, but so this is kind of like the drawback that you cannot really illustrate this in as a three-dimensional figure in 2D, but that gives you this idea. So there's angle theta cut between. So this rotation direction is exactly how you bend, right? So your fingers go along B and you bend along the direction of C. Okay. And of course, this one follows the right hand rule. And if you choose the opposite direction, that's actually going down. The opposite direction will be the negative of B cross. Okay. And indeed, this is actually C cross B, if you think about it. So let's look at this screen once again. So if you do C cross B, what happens? So now my fingers go along the direction of C, right? I want to bend along B, so I have to do this. I have to do this. So my C is to the right, my B is to the left, so I bend like this. Oh, my thumb is going into the wall, okay, into the swing. So that's exactly opposite as what you have done on the left. Okay? So if you use the physical notation, that's actually a circle with a cross. This just indicates that this is like an arrow that's flying into the wall. Okay, so you only see the tail. Okay. So that's if you think about this as a theta angle. Okay, so this is well, in a way, it's kind of a clockwise for the picture on the right, right? Counterclockwise for the picture on the left. But they're opposite because you just chose a different order, right? So B cross C, C cross B, exactly opposite. So it's good. But the bottom line is that they both follow this right-hand rule. So whenever you do the cross, and you want to decide the direction of the cross, it has to follow the right-hand rule. Any questions? Okay, more remarks. One, like I said, B cross C equals to negative of C cross B. Okay, so they are along the same ray. It's just they are opposite. Two, B cross C is orthogonal to both B and C. B cross C dotting B equals 0, and B cross C dotting C equals 0. So here we see, okay, these quantities actually make sense because a cross gives you a vector, right? So whatever inside the bracket here is produced from the cross, which is a vector. So you can do a vector dotting with another vector. That's always fine. But note that if you have something like B cross C dot B, what do you think? Does it make sense? If I'm doing the vector crossing the inner product of C and B. So C dot B is it gonna give you a vector or a number? It's a number, right? C dot B is a number. So is it reasonable to cross the number with a vector B? So not within our definition, right? So this does not make sense. Does not have any valid meaning. So unless you want to define something yourself, but you definitely want to make it reasonable. Okay? But within the context of our course, this thing does not make sense. Remark 3, if theta is the angle between B and C, then the magnitude of B cross C is exactly that formula for the area of the parallelogram formed by B and C. Okay? So the magnitude of B times the magnitude of C times sine theta. Okay? So if you recall, for a dot, it's going to be a cosine, but here it's a calculating the area of a parallelogram, so it's a sine. The magnitude of B cross C is equal to the area of the parallelogram determined by B cross C, by B and C. Examples. So what do you think about the magnitude of B cross B itself? So if you have a vector crossing with itself, then does it form a valid parallelogram that has an area? It does not, right? So they're the same thing. So you're just drawing along the same ray. So it's a zero. So that tells you, okay, you have a vector which has a magnitude of zero, right? So that tells you B cross B is the zero vector. Okay. So the cross always gives you a vector. So you should always remember to keep that arrow symbol above. Another example. So let's look at the standard basis. So we have x, y, z, right? And then we have I along the direction of x, j along the direction of y, and k along the direction of b. So if you're thinking about these three vectors, they are really nice in the sense that anyone is perpendicular to the other two, right? So we do know that I cross j equals k. Because if you think about it, I cross j, the magnitude is the area of the parallelogram formed by I and j, right? It's always a 1, right? So I and j are perpendicular, I and j have magnitude of 1, so the cross will have a magnitude of 1. It's just whether it's a negative k or k. But now ijk will form you it will satisfy the right-hand rule, so that's good. But now if you think about j cross I, so the order is changed, it will get you a negative k. Okay. And similarly, when you do j cross k, make sure to verify that. It doesn't give you I back because that follows the right-hand rule. K cross I QJ, right? We have motivated nicely about the first equation at the beginning of the section, but now for that determinant thing, recall that for vectors B and C, we put there B1, B2, B3, C1, C2, C3. Across. So now we see, okay, for the first entry, we write B2, C3 minus B3, C2. So there's no one. And the indices are increasing and decreasing. So you can just, if you want to memorize, just the increasing for the positive term and the negative term, it's just the opposite order. Right? So that's kind of straightforward. But the second entry is a little bit different. It's B3C1, so it's a decreasing order then increase. But the third entry is increase and decrease. So you can see these two have this same kind of pattern. So you're not allowing for the ith entry, you're not allowing the index I. Right? I is 1, 2, 3. But then the second entry is just the opposite order. So which will see another way to memorize it. Okay. But now here we define something else. We define a determinant of order 2. Follows. So basically, we're just going to define this value to be an order 2 determinant. So it's B2, C3 on the first row, two numbers, C2, C3 on the second row. And then what we do is we calculate it by B2, C3 minus B3, C2. And if you look at this products, actually, this is multiplying the numbers on the diagonal minus the product on the numbers on the off diagonal. Okay. So B2, C3, right? Like this. B3, C2, or C2, B3. That's like this. Okay. So these are on the diagonal. The other two, B3, C2 is on off diagonal. Right. So that's good. So later, if you if you are taking a linear algebra, or if you will take a linear algebra in the future, you will see this again. So order 2 is kind of simple. We only have 2 times 2, that's 4 numbers, and the way we do the arithmetic is that we multiply the numbers on the diagonal minus the product of numbers from the off diagonal. So now, in mathematics, it's always common that you generalize things by just extending the order, extending the dimension. So we are going to introduce the order 3 determinant, but now, of course, for this formula, we want to write it another way. Okay? So then, for every entry, we can express the expression, express the things in terms of the order 2 determinant. So thus, B cross C can be written as so here we can just write B2, B3, C2, C3 right here as the first entry. That's exactly the thing that we defined the order 2 determinant, right? But then we can follow the similar pattern. Just so we want to be we just want to realize that the expression at the second entry is opposite, has the opposite sign. Okay, so we put a negative, but then we still want to put the smaller indices on the left. So B1, B3 here, C1, C3 here. Okay. Now, if you keep it negative, then indeed you will have B3, C1. Has a positive sign on the box. Okay. And finally, the third entry is just going to be B1, B2, C1, C2. It just follows exactly the first entry. And of course, if you can write it in the coordinate form with the angle brackets, you can also write it in terms of the standard basis. Right? So you see, okay, the first entry in front of I, and it's just we're just putting B2, B3, C2, C3 in order to determinant. And then as long as you write this and you know how to calculate the order to determinant, you're good. So you don't really have to memorize the products. That's in the equation on top. Okay? So, any questions so far about order 2 determinant? Okay. Oh, good. So now let's define the order 3 determinant. So define a determinant of order 3 by the following. So order 3 determinant, well, symbolically, so yeah, let's just if you recall, we have at the beginning of the section we have a 3 by 3 object, and then that has ijk on the first row, and then let's just write x, y, z on the first row. So that just represents whatever we want, okay, on the first row. And now the second row and the third row are going to be the entries of B and C. So B1, B2, B3, C1, C2, C3. So the definition of this is going to be x times whatever remains if you remove the row of x and the column of x. Okay. So it's going to be the order 2 determinant that remains multiplying by the x that we start with. Okay. And now we look at, so now for the first row, so we have to do this for every entry of the first row. So now we start with x, and then we have y, right? But y, there's something different. So we minus. Now we isolate y, we eliminate the first row, the second column. What we have left behind is B1, B3, C1, C3 as the order 2 determinant multiplied by 1. Finally, like I said, we need to do it for the last entry of the first row as well. So you see, we have B1, B2, C1, C2 as the remainder, order 2 determinant, right? Times Z. Okay. So this is the way that we define the order 3 determinant based on the definition of order 2. Okay. And somehow you can imagine if you define order 4, then that's just you look at the first row for the first number there, eliminate the first row, first column, and then you have order 3, and you multiply things, and then you minus the second entry of the first row, and then just continues. Right? So this is a really systematic way to define the things. So to put the way that we do the definition, so let me just quickly write the notes below. So how do we get the first expression? We got it from looking at, so yeah, we just look at the first row, right? So x, y, z. So when we look at the x, we eliminate the first row, first column, and we have that order 2 determinant that remains. And now we notice that the sign here is a plus, minus, plus, right? So how are we determining the sign? If you think about it, x is the first row, first column. So the plus sign in the front is because x is the first row, first column, which is a 1, 1 entry. So the sign is -1 to the 1 plus 1. And which is, of course, -1 to the 2, which is just positive. And now, so indeed, I'm kind of cheating because I'm copying and pasting, but that's something you can utilize definitely if you use iPad. What happened? So now y, similar story. So we choose y, and then we eliminate the first row, second column, and now we have B1, B1, B3, C1, C3 in the order 2, right? But how do we determine the negative sign? So that's the same story. For the negative sign, we notice that y is the 1, 2 entry. First row, second column. Okay. And now if we look at -1 to the 1 plus 2, that's exactly a negative one. And of course, for z, it's now the first row, third column, so that's a -1 to the 1 plus 3. Let me also, I can just directly copy. I can directly paste. I didn't copy anything also. When we select z in the first row, third column, that's what remains, and the plus sign is because z is the first row, third entry, third column. Okay, so it's -1. So you see, this is actually a very, very systematic process. Okay? And once again, if you want to define order 4, it's going to be the exact same process. And if you want to define order 5, then just relies on order 4, and just keep on growing. But here, for this course, we just need at most order 3 determinant. Any questions? Yes.
Does that mean order 4 is negative?
Okay.
If there was an order 4, then it would be negative, right?
If there were a order 4, so yeah, let me quickly mention what's going to happen. So on the side, this is actually a very good question that you are trying to extend it yourself, right? So let's just say we have x, y, z, w, and then we have the row of b, the row of z, the row of d, right? And then what we do is it's going to be x times you eliminate the first row, first column, right? So that's the remainder, and then minus y multiplying by what remains. We eliminate the first row, second column, and then plus, and then minus. So that's the pattern that I'm kind of trying to illustrate to you. So X, Y, Z, W, right? So for whatever order 3 that you see, we want to fill out, that's exactly the entries that you get if you remove the first row corresponding column. Okay. So that's about, so and why is the plus, why is the minus? So X is the first row, first column, so this is exactly negative 1 to the 1 plus 1. So Y is the first row, second column, so that's exactly negative 1 to the 1 plus 2. And then a plus, and then finally a minus.
Where are you getting the -1 from?
Very good question. Where do we get the -1 from? That's the, well, the definition. So that's something out of nowhere in a sense. I don't really have a perfect explanation for that, but yeah. So let's go back for this question. Let's go back to this. Okay. That -1 comes from the inconsistent sign that you see in the expression of your cross product. So yeah, we somehow have to introduce something. So otherwise, so yeah, if there were no negative sign right here, everything is nice. We don't really have to flip the sign when we do that definition. Okay. But if there is a negative, then we need to think about something reasonable to formulate everything. Very, very good question. Does it make sense?
Yeah, I'll accept it.
Great. So yeah, well, the thing is, this is something, it definitely helps you to memorize, but it's not really required, right? So whenever you do the order 3 determinant, or whenever you do the cross, you don't really have to do this formula in front of you. You can always do, yeah. You can always do this, which is a little bit longer, or you can just do this, which is a little bit harder to memorize. So in this course, I would say I highly recommend you to get familiar with the order 3 determinant. Because that's just simpler, at least for myself. And also, it's gonna be easier to determine, okay, now you understand this whole process. Okay, so now let's continue. Now, symbolically, so notice that here, X, Y, Z, the first row, they are just symbols. They don't really have to be numbers. They can be vectors. So we can just replace X by I, Y by J, and Z by K. Okay. Symbolically, we have the following. So B cross C is, so we just replace X, Y, Z by I, J, K. Okay. Yeah, let me just keep that part here. So I, J, K, B1, B2, B3. So that's just the entries of the vector B. And C1, C2, C3, that's the row for vector C. And then we just use that top line to be the definition. That's the definition of the order 3 determinant, right? So but we just fill out X, Y, Z. So here I can just cheat by just copying the top row, but let me write it again instead. So if you are just doing the notes on yourself, or just making some scratch, it's always going to be easier if you copy and paste. Okay, so this is exactly gonna give you the formula on the previous screen. Okay, so now as promised, we give you the order 3 determinant equation for the cross product. Okay. But now here is something that's slightly different. So there's an alternative calculation for the order 3 determinant. That's something you also are gonna see in the linear algebra course. So to calculate ijk, so let me just write it again because of B1, B2, B3 for the entries of B in the cycle of C1, C2, C3. So how do we calculate this? So instead of doing so here you see I'm making another copy of the entries, right, on the side. And there's a reason. So to calculate this determinant, we don't really have to stick to the equation above. You can always do the following. So remember when we were doing the definition of the order 2, we have the concept of diagonal numbers and off-diagonal numbers, right? So here, if you start with ijk and just join the lines along the diagonal direction, so you're gonna draw you can draw 3. So this is the first one, B2, B3, right? And then there's the second one that's just next to it, starting from J. And there's the third one that's starting from K. So those are the 3 that you can calculate as a product of 3 numbers, 3 expressions. So that's exactly what I'm gonna write down. So B2C3Y plus B3C1J plus B1C2K. So these are the positive expressions. And of course, there will be negative expressions, right? So what are they? They are the off-diagonal ones. So starting from K, going the off-diagonal direction, that's this one. And then the next one is on the right. Well, I can say actually it's I can say it's starting from the last row is C1 and then C2 and then C3. Okay, so that's more reasonable. But basically, you have at most 3 of these off diagonals, and we just multiply the things along those off diagonals and put them down. But they have negative sign in the front. Okay, so it's going to be a minus B2C1 I minus B3C2. Oh, excuse me. It should be. You see, I'm trying to write according to what I have, but it's just I made a typo, so it's okay. And then so and then minus B1C3J. Okay. So this is an alternative way to calculate what you have from all the 2 determinants. So if you were doing this, then you still need to expand out the order 2 determinants, right? So diagonal minus off diagonal. So you repeat for the other 2. Right? But then for this way, you just you can just write it out just directly from all 3 determinants. Does that make sense? Okay. So yeah, just so if you want to memorize it, is on the diagonal there are 3. There will be positive products, and then for the off diagonal is there are also 3, but they have negative. So off diagonal starting from C1 and then C2 and then C3. Right. So in the bracket, so it's not required, but it's something you know. Example. Find a vector perpendicular to the plane that contains points P has coordinates 1, 4, 6. Q, which has coordinates -2, 5, 1, -1, and R, that has coordinates 1, -1, 1. So basically, you know that in the three-dimensional space, if you pick random 3 points, you can always define a plane, right? So something like 1 point, second point, and third point, right? So that will define the plane that you have in front of you. But in the unfortunate case that this third point is along the line through this first and second point, then that's only defining the line, right? Then you will be able to include another point. But here it looks like PQ and R, they are not really along the same line. So we are able to actually determine it from calculating the vectors. Okay. But essentially, whatever 3 points, so we don't really care about the exact location. Let's just say that PQR. So essentially, they're going to be on the same plane. And we put R here. So it looks like it's lying in that plane. So it doesn't really matter the location, but what we can do is we calculate, let's say, the vector PQ, okay, and the vector PR. So if they are not parallel, so then they are definitely not along the same line, right? But then, how do we calculate the vector that's perpendicular to the entire plane? So I'm going to argue that if I calculate the cross product of these two vectors, PQ and PR, that will give me the red vector that's perpendicular to PQ and perpendicular to PR, right? So that will be perpendicular to the entire plane. Okay. So that's our thought process. So we have PQ. So now PQ. So basically, it's just the head minus tail. So head is Q, tail is P. So Q minus P. So -2 minus 1 is -3. So you should be very familiar with it by now. So the end. So for the second coordinate of Q minus second coordinate of P, that's 1. 5 minus 4. And then the third entry is -1 minus 6 is -7. PR. So of course, yeah, so for PR, let's just write things out explicitly. So it's gonna be the coordinates of the head, which is R, minus the coordinates of the tail, which is P. So 1 minus 1, -1 minus 4, 1 minus 6. 0, -5, 5. So those are the two vectors as shown in the picture on the right, right? So PQ is -3, 1, -7. PR is something else, and of course, just by looking at these, they cannot really be parallel, right? So when they're parallel, you're just saying, okay, one of the vectors is a scalar multiplication of the other. So when you have PQ and PR along the same direction, they're just saying, okay, PQ is some lambda times PR. But that's definitely not the case here. So PQ has 3 entries to be non-zero. PR has a 0 entry. That's not possible for this to hold. So indeed, they are not along the same line. So we are doing the cross. So PQ cross PR. So let's play with that all the 3 determinants. That's actually the favorite way that I personally prefer. IJK on first row. So PQ is -3, 1, -7 on second row. PR is 0, -5 on third row. Now let's just calculate by
the definition. So element the first row, first column, will give you 1, -7, -5, -5, as remains in front of I. Now minus, keep that negative sign in mind. It's always in front of J. Okay. So now eliminate the first row, second column, it will give you 1. So you need to stay focused. Okay. So eliminate first row, second column, that's -3, -7, 0, -5, J plus eliminate first row, third column, that will give you -3, 1, 0, -5. So look. So now, if that's okay, then we just do the diagonal multiplied minus the off diagonal multiplied. That's for the entry of I. So that's -5 minus 30. Assuming 35. Yeah. So -5 is on the diagonal. We need to minus. Now the product along the off diagonal is -5 times -7. That's 30. Exactly. Okay, so that's fine. So far so good. Okay, I see. So minus. Okay, along the diagonal, these two will give you 15, right? The off diagonal will give you a 0. 15 minus 0, J. And then the diagonal, that's again 15, and then that's a 0 again. So now you see, once you simplify, that's the cross product vector. So 40i I minus 15j plus 15k. Okay. So now once we get to this point, it's always nice that we check if this result is the vector that's perpendicular to both rows of your determinant. Okay? Because we are starting with those two vectors, we want to get the I see a question. So here the question is, should the 35 in the bracket I in the I bracket be positive? So okay, so very good question. So here, let's just go back to that order 2 determinant definition. Quickly, right here. So we multiply with the diagonal numbers, that's this, right? We need to minus. That's the negative sign that comes from. We need to minus the product from the off diagonal. Okay, so there's a difference. Okay. So just now we have -5 minus 35. 35 comes from the product of the off diagonal. But then the difference, that's a subtraction, it must be there. That's exactly why. Very good question, very good question. Because it's really indeed a common with that. Okay? So negative is always there. The negative is always there, you see. We are minusing the product along the off diagonal. That's why there's a minus there. So Jason, does that answer your question? Let me put it up. Let me put it here, just in case. So, I hope that answers that question. So now back to the comment. So the results that you have should be a vector that's perpendicular to both of the vectors that you start with. Okay. So what you can do is you quickly do the dot product and check. So the circle is the vector, you dot with the first row, well, the middle row right here and see, okay, we have 3 times 40, that's 120, okay, and we have 15 times 1, which is negative, and 15 times negative 7, which is also negative. So that's 15 times 8, right? 15 times 8 is 100. Okay, good. Cancel, everything cancels out. So now if you do the dot of this result with this row, you expect that's gonna give you a 0 again, because this is negative 15 times negative 5 plus 15 times negative 5. That's also giving you a 0, right? So always, when you get a cross, just dot with the original vectors and check. So the point is, if you it's really likely that you if you make a mistake, it's really likely that you mess up with one of the signs. But if that happens, that you will quickly identify that by just after you check with doing the dots. Okay, so very important. Okay, whenever you do a cross, just double check. So now we can conclude the above is a vector perpendicular to the plane, to the entire plane. And in fact, or I can say any non-zero scalar multiplier of the above works. Okay. So we were trying to find a vector that's perpendicular to the entire plane, right? So if you say I divide every entry by 5, so that's just shrinking it, but still it's perpendicular to the entire plane. Okay. But of course, a cross always follows. So was it good? Yes.
How do you like know that?
The question is, how do I know if the vector is perpendicular to the ordinal plane? Right?
Yeah.
So very good question, very good question. So in fact, what we have done is that, so let me just draw that across. So that's the cross. Firstly, it follows the right hand rule, so PQ cross PR, right? So we do know that this vector is perpendicular to PQ. That's something we just verified this by doing the dots, right? And that's perpendicular to the other vector PR. That's the other vector, right? So now here gives I'll give a claim that whatever vector within the plane starting from the point P, it can be expressed as a linear combination of PQ and PR. So for a two-dimensional plane, you can use any two vectors, non-zero, non-parallel within that plane, and use these two vectors as a coordinate system expressed any point on that plane. So to quick, so let me draw it a little bit shorter. So the argument here is that I just draw from the head two parallel lines, parallel to QP and RP. So this and this components, they will add up to the vector that's PQR, let's say S. Okay. So for whatever PS vector, we can find prime and Q prime along the directions of PR and PQ. So PR prime and PQ prime, now they are perpendicular to my cross. Right? So PS is also perpendicular to the cross. So this is the parallelogram rule that you law that you have seen as the sum. So yeah, very good question. And this is also very important, okay? So as long as two of the vectors are non-parallel within the plane, that are that are perpendicular to that vector in purple. In purple, then the entire plane is going to be perpendicular to the vector in purple. So actually, this is a very good question, but I don't really find students asking this. So very good. Actually, this is the first time I ever have a student asking this question at this point, but that's very important. Okay, that's good. So now, the next example is about the area of the triangle. So we do have another way to find the area of the triangle. Find the area of the triangle with vertices P, 1, 4, 6, Q with coordinates -2, 5, -1, and R with coordinates 1, -1. So basically, it's just saying, okay, I have 3 points, P, Q, R, in the 3-dimensional space. I want to find the area of the triangle. So I think in the homework, you see a special triangle that has some special geometric properties. But now these 3 points are kind of not so, may not have such a nice geometry, right? So, but we still can calculate it. So basically, we have P. Again, we just ignore the exact locations, but as long as they form a triangle, or even if they don't, even if they are along the same line, you are still able to calculate the cross, right? So let's say if we want to calculate the area of the triangle, we always just calculate the area of the parallelogram formed by 2 edges, and then we just divide by 2. That will give us the area of the triangle. So I can say the area of PQR, that's a triangle, that's 1/2 of the parallelogram PQR. Let's call the other corner to be S, that's PQSR. So PQ cross. Okay, so that will do the trick. Okay, does that make sense? And another comment is that it doesn't have to be PQ and PR, so it can be any 2 vectors constructed from the 3 points. So I can say let me just copy the 3 points again. But if I do let's say QP and QR, right? And what you can do is you just extend the parallelogram in a different direction, but the area is, of course, just 1/2 of the area of parallelogram, right? And if you say, okay, what happens if I just do PQ and then QR? So now they look a little bit different, so they're not really starting from the same point, right? But the thing is, you can extend this vector on the right, and then you can form another parallelogram here. So it's always the same area. Okay. So alternative, one-half of QP cross QR works, and of course, PQ cross QR also works, right? So just putting it on the side. So for now, for calculation, I do realize that these 3 points are exactly the same 3 points from the previous example. So we actually calculated the cross to be that's -40, -50, -15, +15. So we just calculate the magnitude here. So -40 squared, the first entry squared plus the second entry squared plus the third entry squared. So what we see from this calculation is that 40 is a multiple of 5, 15 is also a multiple of 5. So here we can drag out a 5 outside the square root. Okay. So that means we're dividing by 5 squared at every entry. Well, excuse me, at every square. So that's a squared plus 3 squared plus 3 squared. And then to calculate, that's actually 5 over 2, square root of 64 plus 9 plus 9. So we end up with 80 in the square root. Okay, so that's the area. But if it's a general, if those are the general 3 points, then you somehow have to calculate the cross and then take the magnitude. Okay. So here, we don't really have to repeat that process. Remark. So we actually introduced two perspectives of the cross product. So for the geometric perspective, whatever two vectors, B and C. Okay. So the cross product is actually the vector whose magnitude is the area of the parallelogram formed by B and C. But the vector is the one that's perpendicular and following the right hand rule, right? So the shaded region has the area to be the magnitude of B cross C. Okay. So this is the geometric perspective. And then for the arithmetic perspective, that's exactly that order 3 determinant formula that we introduced. Okay. So in order to calculate, it's just we just do this exactly. Okay. And of course, these two perspectives, they are another remark. The volume. So the volume of the parallel hybrid determined by 3 vectors A, B, and C is, if you remember at the beginning of the class, we said we have that vector U starting with C, well, excuse me, starting with A. That will be the volume of the parallel hybrid, right? So if you want to write it out, this is actually A, the vector A, starting with B cross C. So B cross C is that vector U. So A dot U or U dot A, that's not going to be the same, but we just take the absolute value to get the true volume, positive value. Okay. So A dot the cross may be negative. Okay. So if you quickly go back to the beginning of the section, what do we have? We have 3 vectors. B and C are forming you the base parallelogram, and then the vector A is just pointing outside of that plane. So what we wanted is that the vector U, which is perpendicular to the impact base. Okay, so and also we were saying, okay, if U has the magnitude as the area of the parallelogram formed by B and C, that would be great, right? And then we can do A starting with U. So that will give us the base area times the height. Okay, so that's exactly why we have this U as the cross, and then we dot with it. Okay. Right here, right? Right here. The volume equals to that desired cross product U dotted with our vector. So, and then we take the absolute value because it could be negative. But the volume is always a positive quantity. So example, compute the volume of the parallel pipette determined by the only vectors A as having a component 1 to -10, B having a component 2, 1 to -1, or C is also angular vector. C is the vector with component 0, -9, 18. Okay, so how do we calculate the volume? So we just utilize the formula above, but we want to make sure, so we basically calculate A dotted D cross C first. Okay? So A dotted with D cross C. And then we know, for the cross, we just put that in the order to determinant form. And A, we just write down the components. So let's just write IJK, okay, in terms of the determinant basis. So it's going to be I plus 4J minus 7K. That's for the vector A. And now we're dotting B cross C. So B cross C, because our by definition is IJK on the first row, the components B on the second row, component C on the third row. So -9, 18. Yeah. So that's by definition, just writing A dotting with B cross C down. And then of course, we want to somehow evaluate this. And then we can do the dot. Okay. So still, by definition, we of course for A part, we just copy the things down. But then for the cross, we are going to rewrite by definition. So if you recall, this vector will have 3 components, where the first component is log I, right? So it's going to be I times the elimination of first row, first column, and then the remainder or the 2 determinants is the coefficient in front of I. Okay. So it's going to be -1, 4, -9, 18, I, and then we remember that it's a minus the remainder if you cross out the first row, second column in front of J. Okay. The first row, second column, if you cross out, that will be 2, 4, 0, 18. So you should be very familiar with it by now. Finally, there's a plus. In front of K, I have all the 2 determinants as well. So now, in front of K, what do we have? We eliminate the first row, third column, and then we will have 2, -1, 0, -9. Okay. So good. Okay, so now, it shouldn't be too hard because now we have both vectors in terms of the standard basis. And we do know that if you have I starting with I, it will give you 1. So the constant in the front of I will be multiplied. And then you just add the product of the parameters before j's, and then you add up the product of the components, okay? Right, so this is gonna be, let's without doing the simplification, we want the order predeterminant. So that's the component in front of I multiplied minus the components in front of j multiplied. Plus the components of k. So the okay, so now a quick observation is the following. So now, if you look at this, we just replaced the I, j, and k as scalars, right? As those scalars in this definition of the order 3 determinant. So we can write it as what? We can write it as the order 3 determinant where we have 1, 4, and -7 on the first row. And then we just keep these numbers, the second row and the third row, just the same. Okay, this is by definition. Of order 3 determinant. Okay. Well, although it doesn't help you with the computation further, but just this is something that's interesting to see. Okay, but still, we want to calculate the value, right? So let's just continue. The black line from the black line above. So now we just have order 2 determinants. We just want to calculate. So remember, for order 2, what you do is you multiply the diagonal numbers minus the product of the off diagonal numbers. Okay, so it's -1 times 18, that's -18, minus the product along the off diagonal is -36, -9 times 4, right? So that multiplies 1, we just keep it there, minus. So now along the diagonal is 2 and 18. That gives you 36 minus the off diagonal is 0 times 4 as a 0. So that's the order 2 determinant, and then we multiply by that 4 plus. Now 2, -1, 0, -8, -9. So these two multiply as -18. The off diagonal multiplies to 0. So now if we look at the numbers, it's tempting to somehow factor out 18, right? Because 18, 36, the 36 is 18 times 2, right? So we do have 18 in every part of our summation. So this is exactly, let's see. So -18 plus 36, that's exactly 18. Okay. Now, minus, we have 36 in the bracket, and that's actually 18 times 2. And you multiply by 4, even further. So that's 18 times 8, right? And the final product is what? Is 18 times 7, because of plus. So you notice, okay, this is interesting. It's 18 times 1 minus 18 times 8 plus 18 times 7. That's giving you a 0, right? So just if you just want to factor out 18, so 1 minus 8 plus 7. That's something we can also write down. Okay. So that's good. So the calculation shouldn't be easy. So, okay, so now we have a 0 as the volume that we calculated, right? So here is a 0, but if you take the actual value, it's still a 0. So what does it mean? What do you think? We have 3 vectors. So basically, if you scroll back to the figure at the beginning of the section, so it's supposed to be the volume of this red thing, right? But now it's a 0. What do you think? Yes.
Two are on the same plane, so it's like a 2D shape.
So it looks like, yeah, we have a 2-dimensional shape instead of a 3-dimensional shape, right? So it looks like this point A is exactly on the plane that's constructed from B and C. Okay? So that's possibly what happened. Okay? So this is actually a very good observation. So if you don't really have a volume, that just means, okay, it's not a 3-dimensional figure anymore, it's just a 2-dimensional figure. So in that case, we call the 3 vectors coplanar. So in this situation, we actually just have one plane that contains every vector. So we contain A, B, and C. So A, B, and C are coplanar in this situation. Okay. In this example. So basically, once again, for a plane that contains B and C, right? If your A just points out of that plane, then definitely you will have a volume when you construct the parallel pipette. But now, since there's no volume that tells you, okay, A is not really going outside of it. So I think we also mentioned that for whatever plane, for whatever vector within the plane, let's say this one, it can be always represented by just 2 non-parallel vectors within the same plane, right? So A is always, in this case, it can be determined by a combination of B and C. Okay, so now another remark. From the red equation that we established within one of the steps, right? So we can write it down formally. So when you put A dotting with B cross C, actually you can write it as all the 3 determinants where you replace ijk by the component of the vector A. So in the future, if you want to calculate the volume of a parallel pipette, you can somehow utilize this formula and start with this order 3 determinant directly. And you also know that if this result is 0, then A, B, and C are coplanar. So coplanar just means that they're within the same plane. Okay. Coplanar. And the reverse is also true, vice versa. So if they are within, if A, B, and C are the 3 vectors that are within the same plane, then if you do this arithmetic, it's gonna give you a 0. Okay, so this is a nice property. So there are some other properties of cross product. So so in this section, I would like to mention that we have the geometric perspective that's saying the cross product is the vector that is perpendicular to the original three vectors, and then the magnitude is certain value, right? So that's the geometric perspective. But in the arithmetic perspective, actually is a little bit easier for us to verify the properties. So the following properties, I'm gonna write them down. Some of them are really straightforward. Some of the other ones are verifiable through the arithmetic property. That will be easier. So I highly recommend you somehow verify some of the things that seem interesting. Okay, so the first one is that A cross B is the negative vector, or is the opposite as the vector B cross A. Okay, so this is something that we know already. So if you have a scalar multiplication, let's say the scalar C multiplied with A, and you do the cross with B. Okay. So when we were having a dot product in the previous section, we said that C can this scalar C is associative, right? So indeed, that's true for the cross products. So you can do the cross between A and B first, and then multiply by that scalar C, or you can just modify the scalar C to the vector B instead. Okay. So in terms of the geometry, you can well, it's not going to be that straightforward because C could be positive or negative. When C is negative, then the direction changes. So it's a little messy for the geometric perspective. But for arithmetic, with all the three determinant, it's not really hard to verify. Okay. And the next one, the distributive property of the cross. So A cross the sum equals to the A cross individual vectors, and then do the sum. Okay. As long as you don't change the order, it's going to be true. But if you switch the order between the the vectors that you multiply with, then that's not true. As long as you preserve the order. So it's A cross B and C. Okay, so it's A always in the front. That's very important. And then if you have a sum crossing with the third vector, you can also distribute this the sum. Okay, so it's going to be A cross C plus B cross C. Still, we don't really switch the order between the cross. Okay. Between the vectors that you're crossing. All right. Next one. A dotting with B cross C. So this is the formula that we use to calculate the volume of the parallel packet, right? And the thing is, so this is the one that you start with the plane formed by B and C, right? Now, if you think about it, why not you form the plane from A and B and then do the cross and then dot with C? So that's also doable, but then there may be a sign difference. Okay, so here I'm just going to write down this is true. So A cross B dotting C will give you the exact same value as the left-hand side. And basically means what? Basically, it just means, okay, if you do B cross A dotting C, that's just gonna give you the negation of the left-hand side, right? So things like that. So this one is particularly interesting for you to verify. Okay, so for all these properties, it's gonna be interesting. I would say I recommend you do it by yourself if you have the interest. Basically, just a arithmetically write down the symbolic expressions for the left-hand side, and also do that for the right-hand side, and just match, and match whether they are the same or not. Property 6. If we have A cross B cross C, so here you see the order is that we calculate the operation within the bracket, so it's B cross C first, and then the result is crossed with A. Okay. So this one will equal to something interesting. So this is going to be A dot C as a scalar multiplying by B minus A dot B as a scalar in front of C. Okay. So this is what's called the vector triple product. So from across, you always get a vector, right? But you notice that the vector is in terms of B and C. And this is actually one of the homework questions for you to verify this is indeed true in our upcoming homework. Let me see. There's another comment. Let me just mention. Okay, so basically on the right-hand side, for instance, you will have a vector with 3 components, right? So basically, whenever you have A, B, C with components, with 3 components, then this is a scalar which you can easily express, and then you just use that to multiply with the 3 components of B. Okay, so there's an expression in front of I, there's another expression in front of J, and there's a third expression in front of K, right? And you do the same to this expression and then the component-wise subtraction right here. Eventually you will get an expression for the right-hand side vector. Okay? And then for the left-hand side vector, there will also be 3 components. It may be a little complicated, and then eventually you just match the left-hand side with the right-hand side. So if you see, okay, the vector on the left, it has the same I component with the vector on the right-hand side, and for the J component is also true, for the K component is also true, then okay, these 2 vectors are identical. So that's exactly what I'm asking you guys to do, like a proof. Is it clear? Okay. So that's the last property. So final remark. So these properties are the ones that are not so hard to verify, and they are always true. Okay? So I would like to quickly mention that for some other formulas that you can easily come up, they may not be true. So for instance, let's say, okay, is the cross commutative? Actually, it's not. So for certain instances of A and B, it may be true, but it's not always true. Okay, so it's not necessarily true. So sometimes it's tempting to write down some reasonable, it seems seemingly reasonable statements, but they must be verified, okay, in order to be always true. So if you look at the formula below, so A cross with the cross of between B and C, this is not necessarily the same as A cross B, then cross C. Because if you think about it, from the equation above, we see this vector is in terms of B and C. Okay, so this relies within the plane of B and C. And somehow you can expect that this product will rely on these two vectors, okay, so it will lie within the plane of that constructed from A and B, okay, so that's essentially not the same as this one. So these things are definitely not obvious. At the moment that we have learned about the cross. So, so the point here is that if you see some true or false question that's about the cross or the dot products, then you need to be very careful whether you have seen it or not. If you have seen it, it may be true. If you have seen it and you remember it's a true statement, then that's true. If it's modified and it's not according to the definition and you cannot derive it, then it's really much likely that it's a false statement. Right. Any questions?